In section 6.4, we're going to prove that triangles are similar by using angle-angle similarity. A few chapters ago we talked about congruency shortcuts for triangles. We're going to be looking at some shortcuts that prove that triangles are similar in this chapter. And angle-angle will be the first one. And we've already talked about if you have two triangles, and I know they have two pairs of congruent angles, what else do you know? Let's say I have two different triangles. Two of their angle pairs are congruent. I have two angles of the first triangle congruent to two angles of the second triangle. What do you know about that third pair of angles? Well, since the angles in a triangle have to add up to 180, if you have two angles congruent in two triangles, the third pair of angles has to be congruent as well, because they would have to add up to 180, and they'd have to be the same number in order to do that, since the other two angles were congruent. And now all the angles are congruent. Now, all the angles are congruent, which, as we talked about in this chapter, for figures to be similar, they need congruent angles and proportional sides. Well, once you have all the angles congruent, we do have proportional sides, and the triangles are similar. So our postulate here is angle-angle similarity. That if you have, and you only need to know two angles of one triangle congruent to two angles of another, then these triangles have to be similar. They don't have to be congruent. Remember, angles congruent in triangles does not mean the sides are congruent, but the sides are proportional. So these triangles are similar. So in this picture, I do have two pairs of angles congruent. You would know by third angles theorem that angles Z and L would be congruent. That's what we talked about here. Once two angles are congruent, the third is 2 by third angles theorem. But we don't even need all three, because two angles congruent means three are congruent, and the triangles are similar. So I could say that triangle XYZ is similar to, remembering that symbol, and if I do XYZ, I would have to do JKL for those vertices to correspond. So angle-angle similarity today will prove that triangles are similar if you have two angles congruent. Let's use angle-angle similarity here. Explain or show that the two triangles are similar, and then we're going to find the variables. In this first picture, the two triangles I'm talking about are triangles QPR and triangles QST. And if you notice, we are given two congruent angles right away, right? They're both 41 degrees. So I have angle, I guess this angle I'd have to do with three letters. Angle QRP is congruent to angle T. I could do that one with one letter. As shown, because they were both 41 degrees. Well, what other angle pair is congruent then? It's actually one of those situations where the triangles share an angle. What angle is in both triangle QPR and triangle QST? And I emphasize that Q because actually isn't angle Q in both triangles? So of course, angle Q is congruent to itself by reflexive property. So the triangles are similar by angle-angle similarity. I have angle Q congruent to itself by reflexive property, and the 41 degree angle congruent as well. Two angles congruent means the triangles are similar. So if they're similar, I should be able to set up proportions to find unknown sides. Now if I want to find x here, I know that the side that would correspond with x would be this 18, right? They're the bottom sort of both triangles. So I know I'm going to compare x to 18. Here's where you have to be really careful. Now x is coming from this side, which is the big triangle. And I notice I'm given some lengths here. But when you're picking x from the large triangle, then this side also has to come from the large triangle. So I need this entire side, because that would come from the same triangle as x. So I have to do 9 plus 5, so 14. Would be another side in the big triangle, and compare that to, remember 18 came from the little triangle, and where's the corresponding side on this triangle would just be this portion, or 9. So let's cross multiply to find x here. I do 9 times x, I obviously just get 9x there, and then I have to do 14 times 18. That's 252. Divide by 9. Looks like I'm going to get 28 for x. be careful setting up that proportion, especially here because the big triangle was this entire side. Alright, next example here. Are these two triangles similar? I'm looking at the triangle here and here. Obviously they're not congruent, they're different sizes, but to prove triangles are similar I need at least two angles congruent. Well, don't I have these angles congruent because they are vertical angles? And notice parallel lines. Parallel lines gives us information about congruent angles, and in this case, angle E, and making that Z shape, and angle J are what we call alternate interior angles, right? They're between the parallel lines, opposite sides of this transversal. They are congruent. By the same token, I have angle G congruent to angle H, alternate interior angles. So I'm going to jot some notes down. We do have alternate interior angles being congruent. Angle G would be congruent to angle H, those I just marked, and angle E congruent to angle J. And actually, at this point, I wouldn't even have to list the vertical angles, though there are. So the triangles are similar. You know what? Let's list those similar triangles. Triangle GEF is similar to, if I do GEF, I did the 3-arc, 2-arc, 3-arc, 2-arc, so HJF by angle similarity, two angles congruent. Really, all three angles congruent means the triangles are similar. So now I can set a proportion to find Y. And I'm thinking what side corresponds with Y in the other triangle. Y is between the 1-arc and 3-arc, so that would be with 6, 1-arc and 3-arc there. Y compares to 6 the same way that, you know what, I was going to pick 18, but I don't have the corresponding length over here, so I'm going to have to pick 10 in the same triangle as Y, and 10 must correspond with 4. Cross multiply. 4Y equals 60, divide by 4, and Y equals 15. And that seems very reasonable. And we're good to go. So using angle similarity to solve for an unknown. We're also looking at, with angle similarity, we look at something called indirect measurement. And it's a way to measure something indirectly, meaning you don't go up and actually measure the length of something, but we can use similar triangles to find some measurements using proportions. So you create similar triangles to measure something that would be impossible to measure. A lot of times we can do this by using the shadow of the sun, or using the sun and the shadows it creates. Because if you think about any particular time of day, like if you look outside right now if the sun is shining, and you look at any shadow formed by any object, the triangles that are formed between the shadow and the object and the angle of the sun would be similar. Because at any given moment, the sun is shining at the same angle on every single object out there. Change the time and the triangles change. But at the same time, we have similar triangles. Okay, we're looking at the shadow formed. And we're going to use indirect measurement that way to measure things that you couldn't just directly measure, like maybe the height of the building. You're not just going to be able to measure that directly, or the height of a flagpole, something that would be impossible to just climb up and measure. So in this example, we're looking at the school building casts a shadow 26 feet long. At the same time, and this is how you know the sun is at the same angle, a student 71 inches tall casts a 48-inch long shadow. What's the height of the school building? So we're picturing the sun, like way up here in the sky, so far away that these angles would be the same. So we look at the shadow off of the school building, very precise shadow here, and we look at the angle of the sun, and we look at this guy's shadow, and the angle of the sun would have to be the same. We also know that we have right angles formed between the building and the ground and the person in the ground, and the angle that the sun is hitting the top of these people would have to be the same. And that's how we know that the triangles are similar by angle similarity. Or I could look at the fact that the angle at the ground would be the same as well. So let's label the parts here. The school building casts a shadow 26 feet long. I'm looking at 26 feet for the length of the shadow. A student 71 inches tall casts a 48-inch long shadow. Here's his shadow, 48 inches. What's the height of the school building? How tall is the school building? We'll call it X. And I know if I compare the heights, the height of the building is X, the height of the person is 71, to the shadows, the shadow of the building was 26, shadow of the person is 48. These should be in the same ratio. So now I can cross multiply and figure this out. Here I get 48x equals, I have to do 71 times 26, 1,846 divided by 48. And it looks like the height of the school building is 38.4. I'm going to go to 2 decimal places, so 46. Notice the person was in inches, but the building was in feet, so the height of the building is also in feet. This is indirect measurement using shadows and the angle of the sun being the same at any time of day to find a missing measurement. So similar triangles are very helpful in indirect measurement, looking at the angle of the sun being the same in a particular time of day. Remember, 2 angles congruent in a triangle means 3 angles in a triangle are congruent, and the triangles are similar. And one more example, if you're playing pool, anytime that you would hit a ball off a rail, the angle formed off the rail is going to be congruent. So if you're really good at geometry, you can be a good pool player, knowing that that ricochet, that angle ricochet is the same on both sides. Sort of like the reflection is the same angle. And because of that, you have similar triangles formed with the path of this yellow ball here. It looks, we only have one angle marked, so it looks like maybe they're not similar, but wouldn't these both have to be right angles here with these triangles? And now the triangles are similar again by angle, because I have 2 angles congruent. So I have similar triangles. I can set up a proportion then and find an unknown. If I want to find the total distance the ball travels, this ball is traveling first along this 28 inches, and then it goes all the way to this pocket along the dotted line. So I need to know this distance in inches to add to this. I know the triangles are similar. You know what, I was just looking. We need to know this x value. I'm noticing that these are in inches, and since I'm finding a total distance, I'd like that answer to be in inches as well, but this is in feet. So maybe I should convert that to inches. Well, I know if I want feet to cancel, I should put that on bottom. And I know that there are 12 inches in 1 foot. So 4 times 12. So really 4 feet is 48 inches. So I'm going to use that as this length here. So now if I compare this distance, 28, to the other triangle, the corresponding side would be x. It's the hypotenuse in both of those right triangles. 28 would compare to x the same way as 20, this vertical distance, would compare to this vertical distance of 48. Notice 28 and 20 came from the same triangle, both on top. X and 48 came from the same triangle, both on bottom. Let's cross multiply here. 20x equals 28 times 48 is 1,344. And divide by 20. And x equals 67.2. And since everything was in inches, so is this. The total distance that the ball travels would be 28 and 67.2 added together. So it looks like a total distance of 95.2 inches. So using angle-angle similarity today, once you have 2 angles congruent in 2 triangles, they are similar. Just set up proportions and solve for unknowns, sometimes using indirect measurement and the angle of the sun.